Hey Ramblers! This video covers chapter 9.7 and deals with what are called special right triangles. Special right triangles are a little bit like families, but we define them more on the angle measures. So the first type that we'll look at is called the 30, 60, 90 triangle because the angle measures are 30 degrees, 60 degrees, and 90 degrees. The second type of triangle is called the 45, 45, 90 triangle, also known as the isosceles right triangle. Both of these triangles come up frequently throughout this course, and you'll also run into them in some of your science classes. So it's really worth taking some good notes, seeing what the ratio of the sides are, and being ready to complete a right triangle even if you know just one side. So they're really, really useful. Take good notes. We're going to derive the formula for the sides for you so that you see where it comes from. Then I'll give you a sheet which I suggest you either take a picture of or somehow get into your notes and eventually have memorized. And finally, we'll take a look at a couple of examples of how you'll use this to solve for both of these right triangles if you're given only one side. Alright, thanks for watching, take good notes, and I hope this helps. Okay, there are two types of special right triangles, the 30, 60, 90 triangle and the 45, 45, 90 triangle, which is also known as the isosceles right triangle. Let's take a look at the 30, 60, 90 first, and I'll derive for you how we can get the sides of a 30, 60, 90 triangle from just starting off with one side. Alright, well, consider that we have this triangle here, where angle B is 60 degrees, angle A is 60 degrees, and angle C is 60 degrees. Now you might recognize that as an equiangular triangle, which makes it an equilateral triangle as well. So I can be sure that all of the sides measure the same length. Now I'm going to call them 2A for the purpose of my derivation, because just as in a coordinate proof, I'm going to be bisecting them. When I drop an altitude to AD, I will bisect BC, and now it will be into two parts that are both length of A. Now when I dropped that altitude, I created two triangles, didn't I? I have triangle ABD on the left and ACD on the right, both of which are right triangles. Now for the purpose of our derivation, we can hide the triangle on the left side. I no longer need to work with, hide the triangle on the right side. I no longer need to work with triangle ACD because I just need the one on the left. So, looking at this, I see that I have a 30, 60, 90 triangle because when I dropped the altitude AD, it bisected that angle at the vertex A. And, of course, it created a right angle with the opposite side. So, what had been 2A is now simply A, and the hypotenuse is 2A. By the Pythagorean theorem, I can solve for AD, and I see that AD is equal to A root 3. So that gives me the ratio of the sides of a 30, 60, 90 triangle. The side opposite angle A is, the side opposite the 30 degree angle is just 1A. The side opposite the 60 degree angle is A times the square root of 3, and the side opposite the 90 degree angle is 2A, which should make a little bit of sense from our work in the first semester. You'll recall that when angles are congruent, the sides opposite them are congruent. That was a theorem we used a lot. And when angles weren't congruent, the side opposite the smallest angle was smaller than the side opposite a larger angle. And the coefficient of A here is of course 1. And the coefficient opposite the 60 degrees is root 3, which is equal to about 1.732. Of course, the side opposite 90 is going to be the largest, and that has a coefficient of 2. So the ratio of the sides are 1 to root 3 to 2, and it's really important that you have that memorized. Okay, let's take a look at 45, 45, 90 triangles. That takes us then to the 45, 45, 90 right triangle, which is also known as the isosceles right triangle. The reason being, of course, that the angles are congruent. The base angles are both 45, and the vertex angle is 90. So if we mark that in, and mark that the legs are congruent, you'll get very used to seeing this. Well, if the two legs are congruent, then the sides opposite them are also congruent. And as we'll see in a minute, we can use those two sides to calculate the length of the hypotenuse. So by the Pythagorean theorem, on the left side we have the sum of the squares of the two legs, and that equals the square of the hypotenuse. Simplifying on the left and then taking the square root of both sides gives us a hypotenuse, xz, equal to a root 2. So the ratio of the sides in an isosceles right triangle are 1a, 1a, and a root 2. Now you may wonder, why am I using a and not something else like x? It's because when we are trying to solve for right triangles, x is often a variable we use. So I think it's better to refer to the common factor between the three sides of the triangle as a. Okay, before we move on, let's make sure we've summarized what the ratio of the sides of these two important right triangles are. Now, when we say ratio, it means that all the sides have a common factor, and we're referring to that as a. Well, the side opposite the smallest angle in the 30, 60, 90 triangle on the left is going to have the smallest coefficient. So the side opposite 30 is 1a. The side opposite the 60-degree angle will be a root 3, and the side opposite the 90-degree angle, or the hypotenuse, will be 2a. In the 45, 45, 90 isosceles right triangle on the right, the two legs have the same measure, and so they will both be referred to as a, and the hypotenuse will be a root 2. Okay, I'm going to give you some examples of how these work when we're given numbers, but I hope you'll note that for both of these, all you need is one side and you're able to complete the entire right triangle. Say we're given this 30, 60, 90 triangle, and we are told that the side opposite the 30-degree angle is 5. Now, can we find the other two sides? Well, of course we can. We recall that in a 30, 60, 90 degree triangle, the side opposite 30 is a. In order to find the hypotenuse, we simply double that, because the hypotenuse is 2a. So this would equal 10. And then the side opposite the 30-degree angle would be a root 3, which would equal, of course, 5 root 3. So now you've solved the 30, 60, 90 triangle. Let's try another one. Can you solve this 30, 60, 90 triangle? Pause the video for a minute and see if you can. Since the side opposite 30 is a, and that equals 2, the hypotenuse will be 2a, or 4, and the side opposite the 60-degree angle will be 2 root 3. Now the problems get a little bit more difficult when the side opposite the 60-degree angle is the whole number. Because now it's not a that equals 5, it's a root 3 that equals 5. So in order to find a, we'll divide both sides by root 3 and then simplify. And we have simplified, of course, by rationalizing the denominator. So a is 5 root 3 over 3. We always try to get a because once we know that, finding the hypotenuse is easy. You just double it. So the hypotenuse would be 10 root 3 over 3. Okay, why don't you pause the video and try to solve this 30, 60, 90 triangle. We know that the side opposite 60 is 4. So can you find the side opposite 30 and the side opposite 90? Give it a try. Okay, so we know that 4, since it's opposite the 60-degree angle, is equal to a root 3. So, dividing by root 3, we can solve for a. And when we rationalize the denominator, we see that a equals 4 root 3 over 3. It's a pretty good shortcut that whatever a is, you can just whatever the side opposite the 60 degree is, you can multiply by root 3 over 3 to find a. Now to get this hypotenuse, we just double that, and we get 8 root 3 over 3. Now the last place that they can give us a side would be the hypotenuse. So if you're told that 8 is the hypotenuse, then you know that 8 equals 2a. So the side opposite 30 degrees must be half that, or 4. And then of course the side opposite 60 degrees will be a times the square root of 3, or in this case 4 root 3. Why don't you try solving one by pausing the video, and suppose you knew that the hypotenuse was 7. What would the other two sides be? Okay, the side opposite 30 is going to be half of 7, or 7 halves. Then the side opposite 60 will be 7 halves over, or 7 over 2 root 3. Alright, let's take a look then at the next kind of special triangle, the 45-45-90 triangle. For a 45-45-90 triangle, once we know that one side is 5, the other leg must also be 5. And then the side opposite the right angle, the hypotenuse, will equal a root 2, or in this case, 5 root 2. Let's see if you can figure out this one. Okay, it's not too hard to see that the other leg will be 2, and that the hypotenuse will be 2 root 2. But what happens when we're given the hypotenuse? And that's a whole number, like 6. Can you find the lengths of the other two legs? Pause the video and see if you can. Since 6 is equal to a root 2, we'll solve for a in the same manner as we did with the 30-60-90 triangle. Solving for a and rationalizing gives us that a equals 3 root 2. Try to solve this right triangle, where we know that the hypotenuse is 9. And of course, it's a 45-45-90 triangle. Set 9 equal to a root 2 and solve, and you get 9 root 2 over 2 equals a. So both of your legs are 9 root 2 over 2. Okay, Rambles, you'll get some more practice in the exercises. I hope this helped.